So next up, we want to replace this code that simply at the minute outputs to the screen and saves as a WAV file to processing the audio so that we can get something like this loudness meter here. So to do that, we're going to use a library called nwave or nwaves. So if we just install that, so in the Avalonia loudness meter, manage NuGet packages, just type nwaves. And while that's installing, if we take a look at documentation, we'll just start at the top, signals. There's a lot of examples as well, so we can look at examples. It looks like, having a quick read over this, and we don't want to dive too much into audio specifics in an Avalonia tutorial, so I won't bore you too much with the details of the audio processing side. That's in our Discord if you're interested. But a quick overview shows that nwaves mostly works with this discrete signal, which is really nice because what you can do is you can chuck a bunch of samples at it, audio samples, any chunk from the microphone, turn it into a discrete signal, and then process the samples inside of that signal and extract things like volume level and using different things. So if we go to, say, utilities, there's like utilities to convert to decibels or to decibel power or from decibels or pitch to frequency. So you can get details from the signals, as well as the actual discrete signal having a few options like RMS and entropy and things like that about the audio. So we don't have to dive into all that code of how to process audio. We're only really bothered at the minute about effectively the loudness, and I'm sure that's pretty much all this is. It's a loudness meter. So once we get the loudness figure, it's just displaying that in many different ways. So you've got the loudness here, you've got the exact same representation of this number here, you've got a bar, the arrow here that kind of looks like it's just a trailing average, so it's a slower response. You've got then integrated loudness dynamics. All these are based on pretty much the same thing, just different timescales. This graph is literally, again, this value just over time. So almost the only thing we need for this entire app to work is the loudness, so the LUFS reading. We know we're capturing WAVs at the minute, or we know we're processing a WAV in a sense. So if we look up what the wave audio format is, you'll see that it is effectively a PCM file, and PCM information is uncompressed and it's 16 bits per sample. So if we bear all that in mind when we take a look at this code, let's see how we convert this raw buffer here of information, which will be PCM data, it'll be PCM audio, and instead of writing it to a buffer, we want to create a loudness value and probably bind it to start with to this value here. So if we do 21.1, so this value here, which is currently just static short term, we will change that to have the actual text. So let's bind that to a property, and we'll call it the short term loudness. Now if we go to the view model, and let's just add short term loudness in there. And let's just put in, to see if it works, -20 LUFS. Compile that, and then this view I believe will update. And let's check we've got a binding. And there you go, you can see it now says 20 LUFS, so we have a binding. So what we want to do now is set that value in the view model. And in this view, I'm just going to make a quick private helper. So private main view model, and just call it mView model. Of the data context. And then we can change these to just view model, which is a bit easier. And in here, whenever we've calculated the value, so we can break off to a function now, just say calculate values, I guess. We'll get rid of the, well, we'll move that in, I think. Just keep that as an uncommented code for now for debugging. So the job of this calculate values will be to do whatever we want with that value. So all this code, which is kind of temporary here, I'm going to move out. In here, we will just chuck in the audio capture device for now. And let's just comment this in here, so that if we ever want it again for now, which we probably will want to. That's why I'm going to keep the comments. We'd likely want to add this at some point back in the future, but it gets it out the way of the main view for now. The writer we don't care about, so that can go. So all we want to do is make a new capture device, in my case on device 1 for now, which is my audio capture device on this computer. When the data comes in, we now want to process it, and then we start capturing. Originally, we started for 3 seconds and stopped. I'm just going to get rid of that delay altogether, move this out of the task so that it stays alive and make it a variable. So I think we just want this to be running, and we won't bother with the using for now. It will literally just get disposed when the application closes. I don't think there's ever a need to dispose of this capture device for now. In fact, there will be when we start changing devices, so let's just move that out of the way. And in the unloaded, temporarily, we will want to then set that to a new device. And because the declaration of this value now is in the class, it won't go until main view is disposed of. So the only thing we'd have to bear in mind, if we wanted to change this capture device, you'd have to dispose of the current one before newing up again. But for now, we just make one, so that's fine there. That also means this doesn't need to necessarily be in a new thread here. So this cleans all this up, and we simply start capturing. So again, let's break this out to start capture and a device ID, just to try and keep the unloaded nice and clean. And then in start capture, this will be device ID. Paste that into there. This becomes device ID. And now we handle the start capture here. So this should all still run the same. Calculate values will actually need the buffer. That will help. I don't think we need a length because buffer always is the length fully. I think we capture it all the time. Just pass it in anyway, just to be sure. In fact, no, we won't, because if we did want a shortened buffer, we should pass the shortened buffer into calculate values. We shouldn't pass the problem down to the next function. But I'm pretty sure it's always the full buffer, so let's just do that. And in theory then, if we run this, I believe it should still output to the console and still work. So let's check we haven't broke anything with the cleanup, and if we have, let's fix it. And there you go, it's now capturing audio, and it's constantly capturing until we close the form. So nothing's broken, and now we're free to try and analyze this data here. So as I mentioned, I did a little bit of research on the audio, and we know the WAV files are effectively, if we search for the word PCM, you'll see a usual bitstream encoder is a linear pulse modulation, PCM, and a WAV is nothing more than a riff, which is a wrapper around a PCM file of 16 bits. So we're expecting to have a 16-bit PCM buffer array here. So if we just comment out the output to screen there, and what we want to first calculate is the total number of samples, because there's multiple samples per buffer. So we'll do var sample count equals, and it will be the buffer's size, which is in bytes. So this is already 8 bits, but you'll notice the PCMs are 16 bits. So we need to divide by 2. So it's the buffer length divided by 2. Get total PCM 16 samples in this buffer. And from that, we'll want to take every 2 bytes and then just divide it by 32 kilobytes to turn it into what a discrete signal is expecting. So we'll make the signal first. The signal equals a new discrete signal, I think it was called. Yep, discrete signal. And you'll see here it's expecting a sampling rate. Well, that sampling rate was in our audio capture here. So we probably want to take the frequency out of there and change it to frequency being passed in. And we can default it to 44,100. And then we will also do frequency or capture frequency here. and we'll default it as well, so we don't even have to set it. We'll make a default value. And it's effectively 44 kilohertz versus like 48, which is higher quality. So we pass in the frequency to the start capture, which should be accepting that. Well, in fact, it doesn't need to because it's part of, obviously, this class. But it does need to be passed in here. Yep, so now we make sure the frequency gets passed in. And when we calculate the values, we know it's always going to be the same value that we are currently storing. And then it needs the number of samples, which is what we've just calculated. So the sample count. And that's it. We have our discrete signal ready to be filled with information. And the last thing to do is loop all bytes and extract the 16 bits into signal floats. So we will do a using var reader, and we'll just make a new binary reader because that has a nice helpful method on it. Memory stream for the buffer. So this just gives us the ability now to use a for loop, nice and easy. We want to loop every sample count. And for every sample count, we want to set the signal sample. So in this case, when you got the signal, it's got discrete samples, and doing an array here allows you to set the sample inside of the signal. This is all on the N-Waves documentation, by the way. So to set each sample, we use the reader and just do read int 16, which is 2 bytes. And that will progress the reader as well in the buffer array. It will go forward 2 bytes, so the next read on the next loop will be the next 2 bytes. So it's just a clean, quick way of going through a byte array and pulling out into doubles nice and quickly. You can do it many ways, but I find this is 3 lines of code and it's done. And finally, just remember to divide by 32,768, I think it is. And that should get our signal into a normal expected signal now. So it's converted it from a PCM16 buffer into a floating point sample. And the final thing for this would be to calculate the loudness value. And to do that, effectively, the loudness value is decibels. So you can see here, it says LUFS, but this is a decimal scale. And it's -3, -6, -9. This is the LUFS scale. So LUFS is also effectively decibels. So all we need to do is get the decibels. If we noticed on the documentation on N-Waves as well, go to Utilities. There appears to be a nice class called toDecibel. So we'll use that, and we just need to get a value. So now to get the LUFS, we'll use the helper class called Scale, which is here, helper class Scale, and it's static, so we can just access it directly. 2Decibel, and now it's expecting a value. So what value do we have on signal? We have RMS, which is probably the one. We have energy. So we've only really got 2 values. We can use the root mean square of the signal, which will be the average, or energy, which I have no idea what energy is. Maybe it's like another calculation somebody else knows. So I'm going to say it's RMS. And with the RMS, calculate decibels. And then let's set the view model dot. We might have to go on a new thread for that, actually. Yeah, we will. UI. Okay, right, I'm in. Dispatcher. .UI thread .invoke. And we will do the view model dot. What did we set it as now? Was it LUFS or something, or short term? Short term loudness equals, and then we will set that to LUFS and insert the actual calculated value. And this should calculate now, if nothing's gone wrong in all that mess. It should calculate the LUFS constantly on every sample and update the UI. And that doesn't quite look right. I mean, it does in a way, but it's not I don't think it's quite right. So if we bring this in, you can see it's somewhere near. Like when you're talking, it seems to be near. So now I'm talking, it's like roughly the 20 value. But it's also when I go quiet. Oh yeah, it is actually. So if you look at this bar's down at like minus 50. Like there. And then when I'm talking now, we're up to about 21, 22. So I think this value we've got here is actually the bar value. And this short-term LUFS seems to be a much more averaged out value. It's not... Yeah, see, the short-term just stays at 23. So look at this one here. And when I stop talking, you drop into like minus 50, but this stays at 20. And it takes a long while. So this short-term LUFS is this arrow, actually. If you watch this arrow, when this drops, this arrow drops. So this is simply what looks like that value over multiple samples averaged out. So we actually have the bar value. So we need to correct that and do a new calculation for this short term, I guess, the whatever the classing as a short period of time. I don't know how many samples, but if we wait and stop, it seems to drop once every second. So if you watch when I talk, this arrow seems to like drop once every second based on the difference. So are you ready? See, like the major drops seem to be about a second. So I reckon if we took the samples for a second, which time scale wise, we're going to have to just run a timer for that to do, it doesn't matter when we get the samples. If the samples stop coming in, we still need to average it over a second. We then need to calculate a new average based on a second worth of samples. And we could do this instead of a second worth of samples. We could just do, I guess, however many samples are coming in. I don't know how many samples are coming in over a second. But it looks like 5 to 10 coming over there. So what we could do is we clearly have, just change that as well. We clearly have the value. We now just need to average it out. So we'll need to do an array of doubles. So if we go into here and chuck in a private list of doubles, LUFS, and then when we are getting the LUFS, we can do LUFS.add the LUFS that we calculate. In fact, why don't we change that from a list to a stack instead? That'll make much more sense, and then we can just push and pop kind of thing to keep 5 to 10 samples in. So in this case, you want to push a new sample in and keep the list of 10 samples. So if mlufs.count is greater than 10, mlufs.pop, and just remove the sample. So I'll just keep a list of 10. And now finally, the LUFS that we want to add. So the average LUFS, our average LUFS equals the mlufs.average. And now we can pass in the average LUFS of those 10 samples. And more importantly, we also want to format that value with a single decimal, I believe. And let's take a look at that. And that should hopefully, well, it will definitely average out the LUFS now, as long as we haven't done that wrong. And it might look similar to the one we're seeing. And if not, I'm pretty sure that's all it is. It's just an average over a certain period of time that we've got to figure out. We did not new up the stack. Equals new stack. There we go. Try that again. And there we have a much more averaged meter. Doesn't seem to be working though. I think we've got the pushing and popping the wrong way around. I think it's never getting a new value. So let's just look at the logic. What have we messed up there? Something's obviously backwards. So we are pushing in the new average, which will obviously come in. The new average is there. The LUFS got 10 in. They're all 53s. We push one in. And so we have the 29, and then we're popping the newest one out. It's the other way around we want to do that. Change that to a queue, not a stack. Got the wrong way around there, haven't we? And then we'll have to just change these, I believe, to the correct terms now, which is NQ, and we want to, in this case, DQ. So that should now do the correct way around. The stack is obviously first in, first out. So the first one you push in is the first one to come back out. A queue will do what we want, which is the oldest one gets pulled out first. So now do we have, there we go, now we have a much more agreeable average. Doesn't quite look right, so let's try and change this to an average of 40 samples. Let's make it much slower. And then if not, I'll leave that kind of calculation up to obviously our Discord server and the audio kind of thing. It's not that relevant to the Avalonia specific guides. The main thing is we have the value. So we appear to have a value there now. And if we wait, it drops off in a similar fashion, but let's watch this drop off first. So they both dropped off to the same value, but this one's climbed a lot faster than this one. So yeah, I think the calculations aren't quite maybe just samples, or if they are, maybe the average just needs to be tweaked. So I'll leave this up to our Discord server to talk about the audio, and we'll fix this calculation to get this LUFS acting correctly. And next we can move on to handling the arrow. So all we need to do on the arrow is to match this value. So this value is from 0 to minus 60, I think, on this scale here. So this arrow literally is this short-term LUFS. We just have to bind it and calculate the size. That's not that hard. And then we want this bar here. By the looks of it, this is an instantaneous bar. So this will be just the normal LUFS that we have. So I believe we already have enough info to almost probably fill out all of this section here now. So if you guys wanted to jump on the Discord who's interested in the audio side, and we can try and calculate all these values behind the scenes and then chuck them in the next video. And we'll move on to getting this bar fully functional, this entire side of the app fully working next. And then we can work on this awesome looking graph here. But hopefully you can see now we have real audio from the microphone, and we just have to figure out this delay in order for the LUFS to calculate correctly, like a short-term LUFS, which I believe is probably, I don't know, it's just as simple as an average, but again, we'll work those details out. But the important information is we have audio and volume awareness now. So that's it for this one, guys, and I'll catch you in the next.